Hey everyone. Hey, so glad you all could make it. Saturday morning. I'm very happy that you found time to spend it with me here today. So before I go ahead and start with the presentation, I want to take time to, thank St. Thomas for giving us the space to have this presentation here, and say a big thank you to Valerie for for organizing the event and for publishing it on the Minnesota Women in IT. And thanks to Minnesota Women in IT for all the support they've given us. And also thank you to Steph from League of Extraordinary Algorithms. He also announced it on his website. And also, big thank you to Applied AI, who made an announcement as well. And I guess the nice crowd here is a testament to all of that getting through to the community, and and all of you showing up here today. And so today our presentation is going to be on retrieval augmented generation and short form RAG, but it's not a piece of cloth, and we'll find out what it means in a little bit. And our agenda here today, I'll start with a little bit of an introduction, and then we'll go into what are language models, what are large language models, then what is retrieval augmented generation, and what's the architecture that goes into a RAG model, and followed with some challenges that are there in RAG and how they can be improved. At the end of that, we'll take a short break and then go in for a demo. By demo, it's rather than just me showing you some code and running it. We will try and have you guys run that code on your laptop. Okay. So before I start the presentation, a little bit about myself. Like all of you know, I'm Sona Maniyan, and I am currently working with Cohesity, which is a backup and recovery software company based out of California. We are a 10-year-old startup, and I am a staff data scientist there, and prior to that, I've worked in a few companies, including Target, General Mills, and Veritas. And I did my undergrad. I did my grad degree here at St. Thomas. I was in the graduate programs for software. It was software engineering. And Okay, so start with an introduction to language models. What is a language model? A language model is it's a probabilistic model of natural language. What does it mean that it's a probabilistic model? By probabilistic, I mean that it assigns a probability to what could be the next word or next group of words in language. Just look at this example that we have here. The chicken crossed the. Almost everyone in this room is going to say road. And why are you going to say road? Because that is the word you have probably heard the most number of times. So your brain assigned a probability to it. This is the most likely word that will come after this group of sentences, and you've said it. Okay, so what a language model does is it tries to make a computer do this, or an algorithm make this prediction. And you have the input, which is the group of words that you've given it, the sequence of words, and you have a model, which would be the language model, and you have a probability assigned, and you choose the one with the maximum probability. So now, in computing, how did language models evolve? Before I show you, we talk about this, I want to show you something. I'm gonna this up and try to do this. Okay, this is ELIZA. I don't know if anyone's all the geeks have probably heard of this, right? Everyone's heard of this. So ELIZA was one of the earliest language models. I think it was introduced in 1966. Probably there's a date out there somewhere in the 1960s. And what happened here was like, you can ask ELIZA any question and it will give you a clever answer, but it will not give you a real answer. It was like a therapist. Okay, how are you doing? Why are you asking me that question? And very generic, but it was definitely a language model. And this is now, the newer language models are more sensitive to what you're saying, and they can use the information to give you better answers. Now, how does this actually evolve? The first, like, a big prior to this, prior to the big explosion that we've had in the newer models that are used, language models were like based on, okay, what is the grammar here, what is the exact word translation that's happening here. It was not very probabilistic in nature, but in the 1990s, n-gram models started becoming popular. So what are n-gram models? N-gram models is like where you have models that capture the order of the words. And even today, these n-gram models are pretty popular, especially in topic modeling. Like you'll see, okay, you use a topic modeler and it generates words that come together. Like if you search for COVID, you have COVID-19 or COVID vaccine, or these are words that come together. You say, okay, n is the number of words in that order that you want coming together. You have 3 gram and models like that. And this was being used a little bit by industry, not as much, but very popular in academia. You had a lot of papers coming out of this, and there was a lot of research that was going into this. And by 2012, 2013, like if people were using Google Translate at that time, you would have seen that Google Translate started getting better. And this was driven by some research that came out of Google, and the open source version that came out was called Word2Vec. And what Word2Vec did was it converted the words into vectors. And there were algorithms that would find how similar the words were. Like for example, a word like apple would be is a fruit, so it has a higher similarity with fruit. And Word2Vec was able to capture this. And that also created a buzz and some momentum, and you had some activity, especially within academia and within like more niche areas in the industry where they were doing topic modeling, and they were trying, it was being applied, but not very extensively, and not like, we didn't hear about it, right? The average person did not know there was something called Word2Vec. So it was definitely gaining popularity, but did not do a big explosion. And then after this was followed by, like in 2017, there was a paper that came out called Attention's All You Need. So prior to this, most of the models could not train extensive amounts of data, but with this particular transformer architecture that came out in the Attention is All You Need paper, we were able to train models with a lot more data. And we saw models like BERT and GPT-1, GPT-2 come out during this period, and BERT, in fact, has been so useful that it was being used in industry, especially like, okay, now tech people were beginning to take notice. They were finding applications for this, and they were domain-specific BERTs. BERT is a bidirectional encoder representation. So that what that means is it doesn't just look at a word in its isolation. It also looks at the surrounding words, both before and after, and it determines like what are the important, which words are similar to it. And so industry is beginning to take notice here. Okay, and then what happens is ChatGPT, and with ChatGPT, what happened is everybody took notice. We've all done a prompt on ChatGPT, and it created the kind of explosion that like the internet. Like suddenly everybody's taking notice of it. They're beginning to find use cases, and but yeah. So this is how language models have evolved, and the version that we have right now is called large language models. Why do we call them large language models? We call them large language models because they have been trained on very huge data sets. And we call talking about common crawl, which is the internet-sized data. The data is what's out there in the internet. And then also some more, like data that's available in other open source repositories, and maybe not even open source, but a lot of data. So this is the unreasonable effectiveness of data. If this was trained on small amounts of data, it wouldn't give us the kind of the kind of performance, the kind of results that we are seeing. But because it's being trained on very, very large corpus, large amounts of data, we are seeing the kind of results, the kind of answers, the responses that we are getting. So when you have these slides available, there is a link to this unreasonable effectiveness of data. So I'll talk about it a little later. And then what has driven, like we talked about earlier, in this evolution of language models, what drove this big growth and this explosion is the transformer model. So we look a little bit into what is the transformer model. The transformer model takes advantage of a mathematical mechanism called attention, and even the older models like recurrent neural networks did have attention. What attention means is that it attends to words which are around that. So it doesn't just, it's not just a word in isolation, but it also understands, it associates meaning for that word depending on what is around it. So like in an example, I went to the bank to withdraw money. It knows that bank is a financial institution. But if I went to the bank, the river bank, it knows that the bank is a river bank and not a financial institution. So attention is the mechanism that gives it the ability to understand this difference. And when we talk about attention, what transformers did differently from earlier recurrent neural networks, which was the model that was used for natural language processing and for language modeling up till then, which is the most popular model, is that they used something called multi-headed attention. And what multi-headed attention does is that it stops being dependent on sequential computing, which was what was important for recurrent neural networks, which meant that suddenly you can take advantage of parallelization. So what happens when you can take advantage of parallelization? You can do more computing. You can be faster. You can put more data into it, and you get a better output. So a bigger model. So here, there's a little bit more here about the paper. The paper was came out in 2017. It came out when it came out. Think about this. Like, okay, this is like how computing is and how open source is. So it wasn't the most celebrated paper at that time. It was only a poster at, I think it was a NeurIPS conference where it came. It was only a poster there. It was not even a presentation there. But people saw value on this, and they picked it up, and it became so much more. So this is the transformer architecture. Okay? And in the transformer architecture, what you have is, this is borrowed from the attention is all you have, all you need paper. And in the transformer, what you have is there's a tokenizer. A tokenizer is, we'll see more about it, but a tokenizer is essentially something that converts these words, the sentences into different tokens that can be consumed later by the model. Okay, there is an embedding layer. What the embedding layer does is it converts these tokens into vectors, and then we saw earlier that that it is not a recurrent neural network, so there is no recurrence and sequence here. So how does the model know the position of the word? There is a mechanism to capture position. And then you have the transformer layers, which are these layers. You have multiple transformer layers, and you have a transformer layer with multiple blocks in it, and each one of the blocks each one of the blocks has a normalization layer. It has a self-attention layer, and it also has a neural network attached to it. That is the feed-forward network. Okay, and then it maps the input vectors to the sequence of output vectors and gives you the response. The transformer architecture, you have, it can be a standalone encoder, it can be a standalone decoder, or it can be both encoders and decoders. And like, I'll give you some examples. A standalone encoder is, a BERT is a standalone encoder model, and whereas decoders are like GPT, where you have an input and you decode the output.
Quick question. So
Yeah.
a token is not a full word. One word may be multiple tokens.
Oh yeah, yes.
So how does it? I mean, I understand there's a position as well, but you have a vector for each part of the word.
Yep.
And how is it useful? And I'm just struggling with the concept of, I understand the concept of word, token, but I don't understand the connection.
Yeah, because they will be next to each other, right? In the.
But it would be a separate vector for each token, right?
Are you saying the token is a syllable or the whole word?
No,
a word may be multiple tokens.
a word will be multiple tokens.
Yeah.
So you have, say you have the word independent. So
Yeah.
think of it as something that does data compression, because you don't want to have a word for, you don't want to have a different token for in and a different token for, like you don't want to have, independent as one token and then in as a different token and dependent as a different token.
Yeah.
So now you're talking about 3 tokens, right? But if you had in and dependent only, you have you have 2 tokens instead of 3. So it effectively gives you data compression here, and later we'll talk about it, because there are some algorithms which make this possible. Okay, and then in the vector space, you will, like, independent, in and dependent would be very close to each other, and when in and dependent are very close to each other, it will be treated as a word.
It will be close to each other because of the position?
Because of the position. Not because of the position in the vector.
Right.
And I will probably get back to you on more details of that. All right, so what does a transformer architecture do differently? So there is, we talked about these pieces, right? There is self-attention, there is positional encoding, and there is parallelization happening. Okay, self-attention, like we talked about, is like the like what we how the word relates to each other, and we saw the example of the word bank. Okay, financial institution in one context and the bank of a river in another context. So that's self-attention. And positional encoding, again, like separates the need for having sequential, the data, the processing being sequential. Now you can do parallelization. And parallelization here, we talked about, how it makes the computation more faster, and you can have bigger, larger models because of this. You can process a lot more data, and you can have a better model at the end of it. And the big advantage here, or the big thing is, it's not like, okay, this is all new things that came about. It's more like, okay, this is a different architecture. It's a different way of thinking about how the data moves how the data is processed. It is not like, there is no new algorithm here. These are all things that came out in the 70s, the 80s, but somebody was smart enough to put it all together in a different architecture, and we have the transformer model. And that somebody is Vaswani and the researchers from Google. So the key question here was, what is a tokenizer and how does tokenization happen? So for GPT and the series of models that we have seen, the tokenizer that's being used is called a byte pair encoding tokenizer. It's a BPE. This is an algorithm that was developed by a C programmer, I forget his name, in the early 1990s. And it was used for data compression. And they found a new use for it, for GPT. And as we see the demo, we'll see which models we are using for tokenization. And embedding, again, is the vector representation. These tokens get represented as vectors, and by embedding it into in a large dimensional space, you can say some vectors are closer to each other, which means these words are more likely to occur together. And you predict the right sequence of words based on how close the words are. For example, the example I gave here is the word tiger is more closely related to the word animal rather than say avocado. A tiger has nothing to do with an avocado. So one of the fun things here is I tried this. The same embedding model we're going to see in our demo. I tried it with the word apple and fruit, and it's pretty close. And if I tried it with apple and iPhone, it's closer. So that tells you a little bit more about the kind of data it was trained on, right? It's trained on internet data, which knows that, which has more references with an apple and iPhone together than it has with apple and the fruit. Now, we talked about large language models, and the models that we are probably familiar with and come up in everyday conversation is the OpenAI's GPT-3 model. Then you have the Llama series of models. For those of you who are newer to this, the Llama series of models is a set of models that have been released as open source models from Meta. And then you have Claude, which is a series of models which have been released by Anthropic, which is another. Then you have Mixtral and Gemini, which is one of the more newer model, which has been released by Google. One of the interesting thing is, if you looked at the evolution that I shared, most of the earlier research came out of Google, and which is expected, right? Because they work with search and so much with language models. And what are foundational models? So these models which we talked about, like Llama, GPT-3, Claude, Mixtral, these are all foundation models. What it means is these are models which have been trained on very general data, and they are models that can be used for other purposes, right? You can build applications on top of this model. They have very general information, and they are not very specific to a particular domain. And even if there could be foundational models which are specific to a domain, again, they would be very generic. They would probably not be a foundation model which has data about your organization. And before I go to this, let's just think about foundational models again. One thing I want to sing is, if you ever try to ask the foundation model a question that is very specific to you, it probably doesn't have the answer, right? I mean, and even if it is, say I wanted to know something about one of Amazon's latest, one of the offerings that, latest plugin that's there in for AWS. I probably will not get a lot of information from a foundational model because there isn't a lot of information on this out there. My attempt at humor here, this is how you ask GPT questions, right? That is the XKCD person. So you put in a prompt, it goes into the LLM, retrieves an answer. So now why this pattern is important, you'll see it later. So I have prompted LLM. I'm a funny person, right? I showed you a fun picture right now. So I'm asking to give me an AI joke, and this is what it tells me, okay? A knock-knock joke. But say I want to know more current stuff, okay? Not LLM be creative. I'm asking, all right, okay, I'm from India, so hey, who won the Indian elections in 2024? I don't have the information. And next, okay, I want something very current. Okay, Google released its newest model, so what is Google Gemini? It doesn't know the information because the training was with data that was trained up till 2022. Now, we want to have a way to overcome this. So we saw that, I think most of you probably have had an experience where you have asked LLM a question and it gives you a made-up answer. And that made-up answer is, there's a technical term for it, it's called hallucination. Almost everybody's probably heard about it. Okay, it's all right when we are searching for something because it's expected, but like say you are on a company website, you're working, you want to know something about your insurance. Okay, the insurance company definitely does not want to give you wrong information. It doesn't want the model to give you a made up answers, right? So you need to have a way to overcome that. And we saw that the model only has information on data it was trained on. It doesn't have very specific data and the data could be older also, right? And again, if you're taking the insurance example, say you're using a foundation model and it has data only till 2022. Hey, you're in 24 and you don't want to know what the policy was in 2022. So we need to have a way to change that, or we need to have some kind of solution for this. And then another thing is, like we discussed about Apple, right? So Apple is closer to the iPhone in our models than it is closer to a fruit. So similarly, when we are talking about, say, medical terms, you're somebody who's suffering hair loss and you want to know about the ways to overcome that. You do not want to know the hacks that some people put together. You want a solution that is more medically, has a medical authoritative source behind it. So how do we make this possible? There are ways, and one is prompt engineering. You can overcome a lot of the problems with hallucination if your model has or is trained on the data that you're looking for with prompt engineering. You can create a prompt that has the right structure and the right words, and you ask the question to the LLM. There is a good, not a 100% probability, but a good probability that it will come out with the answer that you're looking for. So prompt engineering is one solution. Another solution is to do fine-tuning. So what is fine-tuning? We'll get into it a little more in detail, but fine-tuning is just you treat the foundational model as your pre-trained data, and then you create another model on top of that with more domain-specific data. And then the third one, which is the topic for our talk today, is retrieval augmented generation. What is retrieval augmented generation? You can think of it as an extension of prompt engineering. It adds more context to your prompt, and it will use that to retrieve the right information on your domain-specific data. Okay. So before we get into RAG or retrieval augmented generation, let's just talk a little bit about fine-tuning. So fine tuning, like I said earlier, it uses a pre-trained language model. Okay, so you do not have to train a language model from scratch, but you add another layer on top of it. You train another layer with your domain specific data. Like say you are a company that is specializing in patent law, and you want you want to have a model which has information on all everything that's available on patents. Okay, now it's not going to come from your LLM. You need to train it with that. So you take your LLM and you add a layer on top. You train it, and then your users can your users can prompt or query that foundational model and get the answers. Now, when we just say this, immediately what the question is, hey, if you have new data on patents, what happens? You have to retrain the model. Okay, so again, like this is going to be computationally expensive. You need to have the right resources, like people who have technical expertise to train these models, and then there's a lot of testing to make sure that these models are working as expected, and then again that the whole idea of retraining frequently. So it is both computationally and it can be financially expensive.
Question, sorry. Does the training you each fine tune they become public?
No, usually people would fine tuning is done at the organization level. For example, say like we had the example of the patent law, right? So what a company who wants like internally to, what would have probably been done by your interns, or go through a lot of extra documents. What you do is you can ask this model questions, and then use that information, and so it's very domain specific, but it's a fine-tuned model. It's not a model that you're doing from scratch. So a model, if you were to do a model like this from scratch, it would be a lot more expensive than you doing doing fine-tuning. All right. So now we go to retrieval augmented generation. So retrieval augmented generation is like you add context to your model. You give it domain information. But this domain, you do not have to do fine-tuning, or you do not have to retrain your entire model. And it has the advantage of, changing the data at your end. When new data comes, you can use that new data to augment the model. So there are three words here, right? Retrieval, augmented generation. So it augments your prompt with the data that is retrieved from your database or your knowledge base. So you can see the flow here. That is, there's the user query, the context. The context is the data that you supply to the, you augment to the prompt, and prompt is essentially your query, and then it goes into the LLM, and the LLM generates the answer. Okay, the retrieval augmented generation, this it feels like a hack, right? So this actually, in fact, was a paper that was released by Meta when they were FAIR. So FAIR is Facebook AI Labs. I think FAIR Labs is what they used to call them. Like that, there's a link to that paper. It's a pretty interesting, I would say it is a pretty interesting hack, and it's something people would have started thinking of, but they have a very robust, the paper makes a very robust argument for this. And it came out before the whole ChatGPT explosion, so it's a very involved paper. If you have the time, I would recommend reading it. So what are the benefits? Like now we looked at what RAG does, and like how the pipeline structure. We looked at a simple model of that, and what are the benefits of using RAG? The benefits is, okay, you have current information. Next is you you will reduce hallucination because it's using your own data. Like we talked about the insurance, that particular example, it's going to use very domain specific information there, and probably get a much more accurate answer. And it's more easier to train, maintain, and it's cost effective. It's and we'll see how the different components in it work, so that it gives you a better intuition of how these benefits can be exploited. Okay. This is the framework. You have your documents, right? This is your input documents. You will see the word external. Like if you were to read more up on RAG models, the word they use is external data. What that means is just data that is external to the LLM. So it's your domain specific data, it's your documents. It generates embeddings. Embeddings is a way to convert these into vectors. It goes into storage, or it persists that data, and then when you make the prompt, the user query is matched to what information is there in the index or in the vector, and then that's sent along with the prompt to the LLM. We'll look at each one of these components in detail. So the whole action of converting these documents into embeddings, there is a word that you're going to hear when you do this. It's called chunking. Chunking means breaking up these documents into different pieces. Okay, and that's the pre-processing phase. There are a number of libraries out there that can be used for chunking, and I'll give a couple of examples. There's one called Tika. There's another one called unstructured.io. You segment these documents, and why do you need to chunk? Say you have a document which is really, really large, like you have a huge book, okay, and you cannot pass there are limitations to what's the size of the vector that can be stored in a database. So you have to break down this document. So there are strategies that is adopted for this, and the most simple one is to say, okay, I'm going to make chunks of 124 or 100, 500 tokens. So, and then that goes into your database. And another thing that is done with pre-processing is you want to have a way of saying where this chunk is coming from, right? So you augment that or enrich that data, the chunk, with which document it comes from. So that, we talked about this earlier, one of the things you want to be able to know where your source is, where the source of your information is. So this will give you that. And other enrichments are to have, you can chunk the data based on whether there are tables, whether it is narrative text, or whether it's titles. So there are a number of libraries that help you with your chunking strategies. And then the next step to having this document is, by document here we are talking about our internal documents. The next step is to generate the embeddings. The generating embeddings basically is vectorizing the chunks.
I have a question for the chunk. So that the more chunk we create, the better performance will be, or that would be we should balance how to chunk the document?
That's a very interesting question, because that is something it's probably dependent on your data to some degree. So for this particular example, for my demo itself, I tried smaller chunks, larger chunks, and I had one that worked nicely. So I think it depends a lot on your document and how how it's structured. So and even when we are talking about chunk sizes, there are ways to make that chunking more effective. There are some strategies, for example, okay, you do not want to chunk, if you just blanket give, say, 1024, we talked about tokens, right? So one token, if the word is independent, in will be in one chunk and dependent will be in another chunk. Okay, so that could be a problem. So maybe you want you chunk at space points. Where there is you chunk at where there is at the end of a sentence, you tell the you create a strategy which will make sure that the chunk will not break off in the middle of a sentence. Okay, so yeah, so things like that. There are ways to do that to make chunking more effective, and each if you search online, there are a number of strategies, and I don't think anyone's come up with the holy grail of this is the perfect way to chunk. So.
Sorry, so how do you know chunking one way or the other way is better?
There is trial and error, and there are ways to do to evaluate the quality of your results.
So if you chunk too much, for example, you're going to have hallucination, the same way if you chunk not enough? If you do it too much and not enough, you're going to have hallucination?
You might end up having hallucination, or you might not actually get good similarity. For example, say your chunk is very small, right? And you have you're chunking each sentence. So when you chunk each sentence, just think about it, the relationship may be 3 sentences later, right? So that will not be established if your chunk is too small. And if your chunk is too big, there is too much data. Sometimes, and it might not actually fit in your vector DB as well, right? So you're limited by that as the size of the vector as well.
So I'm assuming that when somebody sets this up, they'll run some tests.
Oh,
And
they
say,
will have to
"That
run a
was
number
too
of
big,
tests.
This
Yeah.
was too small.
Yeah.
Okay, now we got it.
Yeah, and this
then
is
they set it up, and then somebody can use it.
exactly. This is not something that is you can do it as a hack like our demo, but even for the demo, like I said, I couldn't hack it just give a number and get a good result, right? So there is some amount of trial and error here and some evaluation to see what is your best chunking strategy. So once, we do the embeddings, and there are different models out there for embedding, and you choose the right model and then convert the chunks into vectors, and these get stored into a vector DB. For our example in the demo, I won't be using a vector DB. Instead, I'll be using the indexer that is provided by the library. But in real life, that doesn't work because you have a lot of data. You want to be able to use a real database for that. So what are vector databases? So everybody is probably familiar with databases. So in our relational databases, we store our data as tables with columns and rows. But in vector databases, the data is stored as vectors. And these what is the value of storing this as vectors? In a vector databases, it has the capability to retrieve the data pretty quickly, and also to most vector databases also come with a way to do the similarity, that is find the chunks or the that are most closest to whatever your query essentially is another vector, right? Which is the chunk that is closest to your query vector.
This is NoSQL. NoSQL DB.
Yeah, so there are, you can talk anything that is not SQL is NoSQL, right? So you could think of it as some of the examples is like one of the earlier companies that made, made a name for themselves or specialized in vector DBs is Pinecone, and they've seen a lot of interest in their database once, this whole GPT explosion took place. And then another one that is widely used is Milvus. If you are keen to learn a lot more about either of this, there's a lot of training videos out there. I personally took a training from Udemy on Milvis databases and how to use them, and like I highly recommend it. It was pretty good.
And one more question. So these are memory database or disk? They store on the disk?
So these, like the one that I used was like, it was on the cloud, so
Oh.
yeah. All right, so the next step here is our big one. How do you establish a similarity between the query that you have given and the data that sits in your vector DB? So what happens is when you give your query, the vector it sends this message to the RAG pipeline, sends the message to your vector DB. It looks for the chunk that is most similar to your query. So for example, I have a query, where do tigers live? And in my database, I have, somewhere it says tigers live in jungles in India or wherever. So it finds that, okay, where do tigers live? It's the most closest one is tigers live in, finds that, adds it to my prompt, sends the data to the LLM. The LLM models it with, whatever natural language capabilities it has, and just tigers live in jungles in India. So it is able to, so this is because we've given this context, it's able to give me this answer. Or in our specific case, we could think about like, if there was a query that was structured in an ambiguous way about apples, and we were talking about apples on a tree, and our database had apples on a tree, it would get that. But if we did not use the LLM, it'd probably bring us the answer. If we did not use the context, it'd probably give me answers about an iPhone. All right. So yeah, we just talked about this, and one thing like in the RAG architecture, one of the additional methods that happen, and almost always it's recommended that you do it, is that you take the top X number of chunks. Because if you're going to take every single chunk, like it is going to either overflow your context window. You can't do that. And the other one is it is probably going to also use irrelevant information, pass that irrelevant information to the LLM. So for example, say, you have only little data in your vector database about one domain, like one specific area, and I'll show you that example a little later in our thing. And say, we are talking about we talked about apples, right? You have only apples on a tree, and you have only 2 documents about apples on a tree in there, and you have a lot of documents about iPhones. So now even even though you did say about apples on a tree, and you retrieved like 10 chunks, only the first 2 chunks were about apples on a tree, and the rest of it was about the iPhone. Even your LLM will most probably still return more answers on the iPhone, right? Because it took all of that irrelevant information and passed it along with your prompt. So you want to make sure that you're taking relevant chunks. So that's why you would say, okay, take the top XYZ chunk.
Is that possible we can use a knowledge graph to index the chunks in the meaning?
Yes, there are ways in, there are RAG models which are, where the vector DB stores data using a graph structure. So even with Milvis, when I did the class, there was a way in which you could use, the search could be using graph, but but one of the biggest challenges with trying to use the graph RAG is that it's very slow. Like graph databases tend to be pretty slow, and that, you have that slowness creeping in. Like there is a lot of work being done at the moment. I think Microsoft has a RAG model, which is like, they call it graph RAG, and I think TigerDB also has some models which are graph-based for RAG. Yeah.
Just in general, the lower part of your diagram, you're showing a set of documents
Right.
on the left side.
Yeah.
And they get processed, and then you have a user query, and then context plus the prompt at the top in yellow.
Mm-hmm.
There's, I presume, the little dotted line over to the right side box where you've got your embedded
Yeah.
query that's going in. And then it flows up and goes into the LLM. Have they talked in any of the documents that you've read about this and the structures, do they talk about what documents you have stored versus what documents you use to train the LLM? They should always be different, don't have any overlap, that kind of stuff.
So that is quite hard, right? Because you're using a generic LLM, like they are not telling you about exactly what documents are used to train. So they tell you they use Common Crawl, they tell you give you some information, but again, when you're talking about what's out there on the internet, it'll be you can't specifically say this document was there and this document was not there, right? So I don't think right now there's a way to make that distinction. I haven't seen any, but
So a good assumption is just statistically, there would be some overlap.
there would be some overlap. Statistically, there will be some overlap. And again, like our example with the apples, there is statistically there is more data out there on iPhones than there is about the fruit. So but because you augment your prompt with data on the fruit, you are more likely to get an answer related to on the fruit than the iPhone.
The way I was thinking earlier in a slide, you said some problems with the LLM is very generic, or you're not using the most relevant source.
Exactly.
Whereas in this case,
okay.
you might be getting at a more relevant source because it's in that lower set of documents.
Exactly. Yeah, your relevant source comes from from your input data or the external data.
And it might be in the LLM.
It might be
training,
in the LLM,
but
but
it's buried amongst thousands
Exactly.
of documents. Here you've got 100 documents.
exactly. So it could be, and that is a problem. So if any of you have tried search engines, looking for very, very specific data, I think when GPT first came out, I was looking for some data on a statistical concept, and I said, okay, I'm not going to use Chrome for this, I'm going to use GPT for this. It couldn't give me the right answer. It hallucinated and gave me something that was totally wrong. And because I knew the concept, I knew that was wrong, and I went in and I checked Wikipedia and then what are the underlying papers for it, and I got the right answer. But because this is not a very popular topic, statistics and some of the theories underlying that, it's not very popular, right? So there won't be that many references to that in the Common Crawl. But say I had used a RAG-based model where I augment, my vector DB or my index data had all of that statistical information. It, similar to my question, it would have found that, okay, this exists in this particular chunk, it would have augmented it with that, and it would have given me an answer in natural language on that.
Also, I know that some web page blog, they mentioned that they can also apply the ranker algorithm.
What was that?
A
ranker?
A ranker,
Yeah.
after the retrieval, they can also get better performance.
Yep. Yeah, we'll talk about that
Okay.
a little bit. Yeah. So I think between the questions that were asked, we've really looked at some of those limitations, right? We discussed some of the limitations of RAG models. So one big limitation is that the LLM will have a context window. Okay, you cannot pass every single thing to an LLM. You cannot pass your entire document set to an LLM. It might be limited, the example I'm going to show has a limit of 4,000 odd tokens. So this can, your relevant information may lie in more than 4,000 tokens. So how you have to find a way to, that's one of the limitations of RAG. Another one is we talked about chunking strategies. You cannot have a vanilla, plain, naive strategy and expect to get good results. There has to be some thought going into it, and there is a lot of testing, and you need to have some expertise to make that work properly. And when ourselves, when we are working on searching the internet for something very specific, we have done this where we've had to refine our query over time, because because we didn't word it correctly, we didn't use the right words. And this can also happen when you're sending a query to a prompt to be embedded and find a similar document. You may not have sent the right information. Okay, like in our insurance example, say your vector DB holds data from different years, and you're saying, okay, what is my deductible this year? What is my deductible? Now, you haven't specified a year in 2024, so why should, it will look for what is most similar to deductible, and there may be a chunk from 2022 which has more similarity to your question, and it will bring back that answer. So because you did not word your question correctly, you are getting the wrong information. So, having a well-structured query is also pretty important for us. There are ways to improve your retrieval, and one is to understand the data, the input data, the data that lies in your vector DB. So to be more aware of the document and the structure of your document, and devise a chunking strategy that incorporates this knowledge. Another one is like he said, it was re-ranking. What is re-ranking? Re-ranking essentially means that you have retrieved, say, the top 40 documents, okay, but you do you use another algorithm to re-rank these documents, not based on similarity, but based on relevance, okay, and so you get a better output that you can send to your prompt. And the third one is you can use a hybrid approach to your chunking strategy, where you add keywords to your query, and which makes the query better, and you retrieve better documents. So these are some of the techniques. There are a lot more techniques that people are trying out. Again, this is something this is not an explosion that's happening in academia, so there is not as much published work as we would like, and as much robustness in the kind of answer, the things out there. You have to test what is out there. It is coming from industry a lot more, and which is kind of unusual, right? For in the last 3 years, so much more has come out from industry than from academia on this topic. With that, I will, we'll take a short break before we go in for our demo, and then, help you all set up your environments for the demo. So, yeah. Okay. There is still coffee and some snacks. Feel free.
And once again, lavatories are down the hallway. Take a left around the elevators, and then come back down the hallway. There's a wall, so you can't come all the way back. But you get to the wall, it's right here on the side. Yeah, yeah. Welcome to the labyrinth of the universe.
actually initialize on the computer network. Okay, I can just use my phone. As long as Collab doesn't have a high bandwidth requirement, my phone's kind of low.
You're seeing the.
You're completely fine.
Yeah. All right. So shall we give it another 5 minutes before we
Tell us
start?
how to get started, because that might take time.
Okay, so Google Collab. So you log in with your Gmail and then go to the Drive, and okay, I'll just show you how it works. Here. All right. Okay, and then you press New here, and go for More, and you can open up a Google Colab notebook. Okay.
Okay, how did you start? Sorry. Good Drive first?
Yeah, Google Drive. You have to be logged into your Gmail or some kind of Google account to be able to do this.
I have noticed that Gmail accounts specifically have more access to things than a Google Workspace, like a custom URL.
Okay, yeah.
Just
Yep.
weird note, but like.
Yeah,
sometimes
Google
maybe it's better
likes
just
it.
to make a Gmail account. Yeah.
Role-based access.
So if anyone's having trouble getting to, and then like once you do this, it opens up a notebook like this. And the notebook is very similar. If you've used Jupyter notebooks, it's pretty similar to that.
Is it Drive? You don't have Collab?
Okay, like, yeah.
Is that Google Collaboratory?
Yeah, exactly.
So you have it on your
Oh, no, so.
You notice that 2FA for Google makes you open like something.
Oh, do you have that? Okay.
Well, the problem is, I have too many devices, so if I leave my, so I also have a little tablet. If I leave that at home, then I can't sign in because it tells me to open.
Oh, open it up at home. Oh.
I can show you what to do, but I cannot do it.
Come on, I
I
opened
don't have
it.
that option.
My system used my phone.
I don't know. Yeah, it's crazy. Yeah, so I searched for it, yes.
Yep, a pin or your face.
Yeah, I mean, the pin is like a simple thing.
I'm trying to explain to engineers, software engineers, this idea that you can represent a chunk of text by a vector of numbers.
But I thought, isn't that very intuitive? Because at the end of the day, you're that is how software works, right? You're representing, you have a underlying representation, right? It is not represented as a word. There is some sort of compression that makes it read it as binary, right? So there's something happening. So a software engineer should naturally understand that, right? Yeah, probably it is more harder for a front-end engineer to understand because you don't see that at all. That's because you work on MSDP all the time, right? Like you're talking to binary. Yeah.
I don't think I'm gonna be able to actually sign in there.
You can't? You sign out of your Veritas account.
No, they,
Oh, they're not letting you.
they don't want, they're not technically supposed to use their Google.
Oh, you can't open your Google
But-
from.
But no, Google's complaining that I will
But not giving you access.
Yeah, if somebody.
let Chrome have access to my passwords. So they disabled that, it was working fine, so they don't want us storing any passwords in
Oh.
browsers anymore.
Okay.
some sort of SharePoint site.
You could just click and roll
Like
it to
softsafelinks.com
and
is like, that
you'll
sounds
get
like
the
Right,
Microsoft.
All right. Okay.
It's not Microsoft.com.
Shall we?
Yeah.
Okay. Right. All right. I hope everyone's been able to open up a collab notebook. Okay. So before we go into doing a RAG model, what I'm going to show is an example of how you can take a document from the net and transform that into like a data set that you can use to put into your vector. You can do for embedding, okay? And this will like help us test whether you have everything installed. Your environment's working okay. So for this, like, okay, the fun thing about Google Colab is each time you use it, you will have to install all your libraries, okay? You do not have it pre-installed like you would be doing on your laptop. So we will be doing this pip install. And okay, and if you notice on the left, there's a folder here, and it will have sample data in here. So you can put data for the time period that you're running your model. You can put data into this, and after that, like, it doesn't persist. It will disappear once you close your Collab notebook. The session's over. So what I'm doing here is I'm saying, hey, I want to install these two libraries. That is the URL lib2 and markdownify. So what URL lib2 does is under the covers, it goes and fetches the particular data from the URL that I'm giving it. And what markdownify does is it converts that HTML file to a markdown document. All right, so we run this. Oops. Yeah.
Can you make the font bigger?
Oh, how do I do that? Let's see. Yeah.
You did Control Plus.
Is that?
I got the same errors.
Okay, I think this should work. I made this work earlier and it did. Okay, let's see if it does. I don't know why URL lib2 is, okay. Let's see if it did import both of it. Okay, and then I'm creating a data file inside, okay, here, like, okay, you have to create a folder called data if you want this, if you want your code to look exactly like this. And then once you've done that, you can run this little guy out here, and inside my data folder, I right now have Treasure Island as a markdown file. Okay, okay. Is this becoming a little difficult to read? Anything? What I can do is I can share this, and we can put it on the like on our event website, and then okay.
That would be better.
All right, I'm gonna open this up. Anyone with the link, okay, and done. So, Valerie, can you share it in our?
So you'll have to share, like, copy the link.
Okay,
and
send it to you.
Yeah,
Okay,
yeah.
let me do that.
Just reply back to that email I sent you.
Ah, okay.
Will that show up in the meetups or where will we find it?
I will, when I send the follow-up email today, it'll be
Oh,
in there.
perfect.
And I'll also
Okay.
embed it in all the metadata.
All right. And then there is another. This is the one example, and okay. Then I think we have. I'll also share this one. Nope.
Are there any costs with Google Colab or just use it to your heart's content?
Yeah, this is fun because when you're using the CPU, there isn't a lot of cost associated. You'd probably be able to do everything you want. But when you use the TPU, like after a certain amount, it times out. Sometimes, like I had to do multiple versions to get this code running in such a way that like it stays within that free, like I get one run within that free TPU. But I've also, because I was doing the demo, I went ahead and paid $9.99 to get some extra compute. And like it's $9.99 per month, so I can compute to my heart's content for this month.
Got it.
But so can we post it now in the event along with the event so that everybody can access the?
Yeah, is everybody on Meetup?
We can.
Yes.
Yeah.
Yes.
And this, let's see what was the? Yeah, for this one, right? Just can you see, or like, do I need to? Sorry about that. We should have got that. Yeah. WFEGORGM. It's from the university, CUNY, and it's got that. It's got that one file that we needed. Okay. I might send you a couple more documents later on, Valerie, because as we get on.
So can we can
Was everybody able to install the libraries?
Yes.
Not here, the two, but Markdownify, yes.
Okay, but
It gives the error,
but the next step actually works.
Okay.
Okay, so I don't. Yeah.
where can we get the link?
Hmm?
Where can we get the link?
Oh.
This is just Google Colab.
Oh, okay.
So you open up a collab notebook and then start.
Just copying what's on the.
Yeah, exactly. You should be able to do. Yeah.
I'm getting a can't access item when I click the link.
Oh, are you getting a share request?
The link from
Oh,
Meetup that Valerie
okay.
just posted.
Oh. All right. What's your email?
Malena, M-I-L-E-N-A.
Let's see.
Dot Higgins,
Dot Hi.
Yep. I-N-S.
Okay.
At Gmail.
Okay. These are portions we'll edit out. Okay.
Can you also send me?
Okay. Okay.
MUU? That's all.
Is that you?
Yes.
Okay. All right.
Thank you so much.
Yeah.
Yeah, I'm getting so this one is not installed.
I did.
It's not G, zip, it's not like install, not G zip.
Thank you. Surprised with GZ one.
They can't access the Google Sheets.
Oh, yeah, I noticed that. Can I give you log in here?
Maybe the settings didn't save.
Yeah.
Like if you didn't save the sharing to everybody.
Okay. I'm just gonna let Lara do this.
Perfect, thank you very much. No, can't access it.
And it's in Tuesday. Okay. So when you like, put that in your Gmail.
get it.
On your Gmail app?
Yeah, it's just coming.
You can rating there.
Yes. Okay. 90.
Nope, 20. Okay, thank you.
Okay. So we all went through step 1.
I'm still not able to get it.
Really?
Can't access. And I tried.
Okay, let's just try getting you the. Are you able to open?
Yes.
Yeah, we have access to denied
Okay.
here too.
And
Okay,
okay,
what's the
let's
name of
just
the?
try to do the.
The error I'm getting is when I go to, this is the link gallery posted.
Okay, so they might be
Google
called.
Sheet, and it's,
Yeah.
and I watched you type it in, and you typed my email, correct?
Yeah. Okay, so but let's try to do it without the Google Sheet.
Right, no, that's fine.
Can you try and import these two libraries now? Press mode.
If you don't.
And get a new sheet. Okay.
Oh, I see, I'm doing the second part.
Yeah.
If I just like change it, right, but then I
You
just
are-
click done, it doesn't update.
Yes.
They're not really-
Amma?
Yeah.
What is the name of the
Okay.
Google Sheet? Like, what's the name of the data sheet?
The sheet is called. Is it called a presentation? No, it's not a sheet. You have Google Drive. The link that we got. No, but you have Google Drive, so you have to share it. Okay. It's called a presentation.
So this is my drive.
I don't have it there.
There, and the second one. Right.
Okay, so, the relationship I'm trying to report to this is.
Okay, can you just do copy link? And can you send it to Valerie? Yeah. She can replace that. Okay. All right. So just to get us moving, if we did the import, did we do the import like, is it import working for everyone? Awesome. So, I mean, any URL that you guys think, go to one which has a document that you are interested in, and then you can get that.
Can you explain us what?
Okay,
are
so
you
what's
trying to-
happening here is
Filtering.
I created a, here, what I did was, this is my, this is a folder that's already there in the collab. Okay, it has some sample data. I created another folder there called data. How I did that was I went here, I pressed on this, and I said, hey, new folder, and I gave it a name. I called it data. And then once I'm telling this, this is the list of URLs. So here I've done only one URL, but if I want to do multiple data sets, I can do different URLs. So I did URL list here, and I said, hey, this is just some steps to name the files accurately, and it goes in and it does a markdown of this. This is in HTML format, and it will do a markdown, and it will create a file, treasureisland.md. Okay, and if you open this, I think. All right, it does have that Treasure Island here. This is Toaster Oven. Somewhere around this, it did have that. Okay. Or maybe this is a technical description. Okay. But, okay.
So you're reading from there and storing this file?
Yeah, storing it inside here. Okay. So this, I think this is the wrong link here. It used another link earlier. Okay. But I think I took this is probably the wrong link. I took this from the Gutenberg project. It has several books in there. And if you go in and look for that link, you'll find a link to Treasure Island, and it has the entire book in there, and you can take that. And that's pretty useful for what we did, what I do later on. Let me see if I can just share this data set. Yeah. What happened? He's still not able to.
No, I say Gemini writing code for me.
Gemini is writing your code for you. Awesome. All right. So, okay, this is just like how do you create a markdown file? Okay, this is one of our steps just to make sure that everything's working. We have all the Google Colab set up and everything. And now let's go back and bring our actual code, which is the RAG. All right. Okay. I think for this to be okay, we will need, like, the best way to do this would be to share this. Valerie, can you give me your
It's the third one down.
third one? Okay, awesome. So I'm going to share this with you. Okay. And I am going to see, I've done anyone with link here, so you should be able to access this. Okay, it's done. And Valerie will post the link. Are you able to access it? Let's do a test.
Good call. Yes.
Okay, so then anybody with the link should be able to access it.
It is on the Minnesota Women in Tech meetup.
Okay.
Only the first one.
So did we remove the old link?
Yeah.
Okay, perfect. So,
Okay.
all right, awesome. So everyone's able to access it now.
I'm also posting it on the League of Extraordinary Algorithms chat.
Thank you.
Is it basically what we were doing? It's not that. So
No, it's not that. That was the first one just to help us get set up. Okay, with the Google Colab and everything. Okay.
the link that was just shared, is that to what we were with?
To the RAG model.
Okay, click on the new. I click on, oh, here's the right one.
There we go.
You ready to new one?
Okay, brilliant. Okay, thank you. Sorry.
It's all perfect.
I need to ready to generate.
All right, so we can get into the exciting part now. All right. Okay, one thing I would advise everyone to do is go in here, click on this. We want to use T4, okay? So you do change runtime, and then you go and click on T4 GPU, okay? All right, save. And
Got it?
okay, and for the right now, I'm going to access the data set that I need from my drive here, from my drive. Okay. All right. Okay, first thing, we install all the libraries we need. So the main library we rely on is called Llama Index. Okay, you will have heard quite a bit about LangChain. This is very similar to LangChain. And Llama Index, what it does is it has a lot of wrapper functions which make it seamless to access the data, seamless to to use LLM model, everything. Okay. And for the time period of our, for this session, for the demo, we can use my login, okay, here from Hugging Face. But what you would need to do is you can go into Hugging Face if you were interested in like using some of the other models. I'll change this right after our demo. So you go in and you you sign up, create a login, and then go into your profile. And in the profile on the left, there's a way, there is a place where you can create tokens. Okay, and that token will help you access any of the models that are there on Hugging Face. All right. So first, while we are talking, one thing we could have done is pip install all of this because this takes a little bit of time. Okay. Right. I ran it earlier, so probably a number of them. The fun thing about all of these libraries is they're constantly changing. So you try to run this code maybe 2 weeks from now, it's going to break because something changed in the library. Okay, so you just go in, look at the docs, and figure out like which slight improvement to the library you need to import. Okay, because when I was trying to set this up, I thought this is going to be super easy. All I need to do is go and understand code that somebody else has created. I take it and I put it here, but surprise, surprise, it didn't work that way because everything broke. And then I had to go into the docs and find out where it broke, why it broke, and make the changes accordingly.
Maybe
Okay.
you can lock in the version.
I can lock in the version, like I can pick up like a particular version, but here what I've done is like, because, the interesting thing about locking in the version is if you lock in the version and you have another version that something else does not work, is not compatible with the newer version, and then that can also sometimes break. And that's how new this domain is. So, yeah. So we've got everything to run. I hope everyone's got that first part to run. And I'm suppressing the warnings. Reason I'm suppressing the warnings here is simply because it gives me a lot of warnings. Newer libraries, a lot of warnings, something is not compatible, but I've tried this, everything works together. All right. And this is like a toy example, right? So, yeah. So what I'm using is Llama Index. When you go into, if you look at other examples which are a little older, you will see all of these are being imported directly from Llama Index. This core wouldn't be there. So one thing to know is, if it's not working, one of the first things you can do is try and add core because they've changed their library to be that way. Right? We import these. Okay. And while that's importing, we can take a look at the prompt that we sent to the system. So it is always recommended that you prefix your prompt with, a very professional approach to getting your answers, because sometimes you get like not so you're not with, you're saying, okay, helpful, honest, respectful. Okay, it's doing all of that, hopefully, right? If you don't do that, you don't know for sure. So, I'm very funny today, right? Right, so okay, you do that. You created your system prompt, okay, and a variable for holding that. And here we are importing what is a prompt template, and the template is this way. You have the user, the assistant, and then you have this. This is the this is a placeholder for where your query string will go. Okay. And this is the login that I'm using from Hugging Face. And like I said, you can go in and create your own token for this. And what that token does is it lets you use some of the, for me, I wanted to use Llama 2, and having this token meant that I could use that particular model. I think the embedding model is something, that you can use for free. But this particular, the language model, you need to have a token for it. All right, so this thing, you probably don't have this data. This is, let me, okay, I'm going to run this. I don't know if you will be able to access it. But you probably can't, right? Yeah, because it's in my drive. But yeah, let's just run it, and then I'll give you access to it once it's run, okay? So what's happening here is it's just, there is a helper function called simple directory reader, and it's reading the data from that directory. Okay, and that comes from Llama index. This is the embedding model. This embedding model, sorry. Okay, this embedding model is a Hugging Face embedding model, but if you look here, this is again something that Llama index makes it easy for you to use. You do not have to have like, you know, another way to get it. You can get it directly from Hugging Face using Llama index. So this is the it's called all MPNet base v2. This is the one where, you know, I told you I tried with Apple and iPhone and Apple and Fruit, and it had better, you know, better closeness with iPhone. So
the document, the one you read into the documents.
Uh-huh.
What's the format of that?
That is the document that will go into the vector. That is my the external data.
Context.
That's the context.
Yeah. Okay.
Yeah. Right?
So it's a text file.
It's the text file. So that was the one that will get chunked, and, you know, all the other steps that we looked at in the RAG model will happen on that document. Right?
So we could just feed it any file.
You could just feed it any file. So you don't have to use my document here. If you want to get exactly the answers that I've got, probably need that, but otherwise you can just feed it any text file. So if you have a text file handy, just good. So okay, this is actually our LLM model, and as it runs, it takes a little bit of time to run. So while it's running, I'll just tell you what are the parameters that we are using here. Okay, this is a context window. Okay, that means it's the maximum number of tokens that are available for input. So your context, your input size cannot exceed that. And then the maximum new tokens is the number of tokens that generates. And then we talked about this hallucination earlier, right? So if you wanted to hallucinate a lot, you can put your temperature as a high temperature, like 1. Here I've put it as 0 because I want it to be like more, you know, I want it to be objective. I want it to take my data.
Dramatic, not random, right?
What was it?
So,
Oh, you want it to be dramatic?
yeah, so that controls the amount of randomness, right?
Yeah, the randomness to the model. So it is like right now there is no randomness, right? It's going to try and be very factual about what it's. But if it's like I'm telling it to tell a story using the context from my, you know, my documents, probably I can put a high temperature there.
You should call it creativity.
Yeah, exactly. It is the creativity index, like how creative can the model be. And yeah, the system prompt is the system prompt that we looked at earlier. Query wrapper prompt is it contains the placeholder, the query placeholder we looked at earlier, and then the tokenizer name is a tokenizer. You wanted to use the same tokenizer that's used by your model because it's being passed to the model in the end. So you would give, like if you look at this, I've given it the same tokenizer and the same model, right? Then the device map. Device map is like a way to tell the LLM which device to map to, and by putting auto, if there is CPU and GPU, it maps to the best device that's out there. And the length, maximum length of the tokenizer is here, and then the this is interesting. These are the parameters I have passed to the model to do quantization. So quantization essentially means you are reducing the precision, the floating point precision of these of the vectors there. So what happens is like a higher precision, more computing, right? So what happened when I tried it without this earlier with the T4 was it was timing out. I was not able to generate the answers. Okay, but when I used quantization, here the library is called Bits and Bytes, and it's a quantization library for CUDA. So it did a good job, and and it didn't. When you reduce the precision, one thing you're afraid of is whether the model would generate accurate answers. But in my case, it did. But probably where you have something which is very, very, you have a lot of things which are very close, you probably have to do some trial and error and see if it's, quantization reduces accuracy a lot. Okay, so our model ran, and okay. So the first question, you remember we asked GPT about who won the elections in India. It was in 2024. So this model was trained, the Llama index model. I think the Llama model, Llama 2 model came out in April. So April or May, and what it does, it did not have enough information at that time to tell us, what the results of the election was. So that's what we are trying to do here. Is one of the documents that I passed 2 documents into the model. One document was the Treasure Island file. The other document that I passed on was a very short document, which a text document with results from India's elections. It was something I took from one of the news websites, and I converted it into a document and put it in. So I'm hoping by doing the RAG model, we'll be able to get more context-aware response. The service context is like a catch-all. It's a function which tells the RAG, okay, what is the chunk size, how much overlap is there, and which is the LLM model that's being used, and what is the embedding model. So why do you need chunk overlap is because you want to give a flow in case 2 documents are pretty similar. You want to give a flow from one to the other. So for example, like if you had my chunking strategy is very simple here, right? It says 1024. So the word we looked at earlier was independent. So in could be in one and dependent could be in another. But I want the when the similar chunks are extracted, I want some way, if it's important and if it's similar enough, for these 2 chunks to come together. So by having the overlap, I am hoping that there will be a way for this to come together if it's an important chunk.
How much is that measured by? Is that like characters, bits?
50 tokens.
Tokens, okay.
Yeah. Okay, so the next one is the vector store. Okay, now I want to, here I'm not using a vector database. That'd be too much of a heavy lift. But for your POCs, you can use the vector store index that Llama index provides. You say, okay, this is the document, and follow these rules. Okay, chunking size is 1024, 50, this is the LLM model, this is the embedding model, okay? And it's doing that thing. This should be fairly fast. Okay, and then I have a query engine here. Basically, it uses the index. It does it takes the top 2 chunks when it's retrieved and uses that to add it to the prompt. So, okay, this is my query engine. Okay, and the query engine has has two components to it. We are not seeing the underlying components, but what it has is a retriever and a response synthesizer. The retriever essentially pulls the data from your DB or your vector index, and the response is it sends it to your LLM to generate the answer. Okay, and now just to understand, okay, what were the top two documents that was pulled from the index. I'm using the same question that I'm going to send to the LLM, who won India's elections, and I'm looking at, okay, what are the top the top 4 documents that are displayed here. When the word node here essentially is the chunks, okay, or the top chunks. So if you look, this is the document I had on the elections in India. It was a short document. It has a 0.69 similarity. It's a high similarity. The other chunks which were retrieved were from the book Treasure Island, and it has very little similarity to my question, right?
What's the definition for the similarity? Is that just
so
similar each other, or just a question and answer similarity?
The chunk being similar to the question, right? Like, okay, which is the chunk which has the nearest, like in semantics, like which has the nearest.
It's comparing the embeddings.
Yeah.
Okay.
So if there's a match to me, these two sentences, if there's sentences very close, similar, I mean these two sentences are very similar. They have the same meaning, right?
They are very similar in the vector space. It doesn't necessarily mean that they're very relevant to each other, right?
Okay. I mean, the process of creating the vector embedding, if the process of learning the embedding is trying to, if some sentence is similar to each other,
yeah,
they should be very close.
They will be very close. Yeah.
What metric is it? Is it the cosine similarity?
So I am not sure what they're using under the covers here. Like for most of the vector DBs that I looked at, I think they use some kind of nearest neighbor similarity. I also know that like cosine similarity is the most popular one. I've seen an example of a RAG model, like where it was trying to teach us what is a RAG model, and they used Jaccard similarity for that. So there are different similarity measures, but the most commonly used one is cosine similarity. All right. So we did this, and now we go in and we actually use that query engine which we created, and we are going to get the response and see if the LLM gives us a better response because we've given the chunk. Okay. So it does this whole thing, and my text was before the government in India was formed. The most recent government in India was formed. So it is, they won the elections, gives us some more details about like, okay, how many number of seats, and the other parties had so many seats, and because of that, the current prime minister will have to form a coalition government. So, which was a lot more than, okay, I do not have the election results. Right? Yep.
So you said your text was
Again, the timing thing, right? I took a new snippet from before the government was actually formed. The election results were declared, but the government wasn't formed. So because they did not have an outright majority, they had to form a coalition government.
So the context you provided, it was post-election.
It was post-election, but it was pre-government forming. Like, in the sense, like, they had to join, like, it's not like the United States where you have one president. It's a parliamentary form. So it is the leader of the majority in the parliament who would form the government. So the majority went to the BJP party, but they did not have a clear majority, so they have to form a coalition government. So the document said that, it picked up all of that information, but it did not say that this person became the prime minister,
Sure.
because it
Sure.
did not have that information.
So, yeah,
Yeah.
I see the reasoning that it formed, I gotcha.
Okay.
Thank you.
All right, I think done with the demo. Okay, thank you. Yeah.
Just scroll all the way to the right.
Yep, that is all the way to the
Oh, it
right.
says user.
Oh, user is like, it should actually,
Oh, so it's a prompt?
yeah, it's a part of my
I'm not
prompt.
sure if they had some, traditional-
Ideally, we should be able to, like, I mean, I have to do some more, some more coding here. You should be able to get the document, like if it had a document name, it should be able to tell you which document it was retrieved from. That's the, adding the metadata to.
If you change a document now that says something very different, the LLM doesn't remember anything about
Oh, it shouldn't remember anything. The way it is not set up to
That's right.
remember is, yeah. All right. Okay, I think if you go in for the T4, like that particular runtime, you should be able to run this without having to subscribe to, the $9.99 subscription. So, okay, yeah, as long as you don't put in a lot of documents. Like you can do a toy example with this. Yeah. All right. I hope you all had a nice time.
Yeah.
And this is useful.
Yeah.
Yeah, thank you.
All right. Yeah. Okay. We are at 12. So. Yeah. Thanks everyone for joining, and thanks Valerie for setting this up, and thank you Steph for posting everything. So.
Thank you so much.
Thank
Yeah.
you.
Thank you.